What up, folks? Welcome back. You're watching J2ME in 2025. So, in the last video, we made this bouncing red ball, and we noticed there was an issue with the frame rates, whereas this was running fast in fast devices, but the frame rate started dropping when we ran it on our mobile. So, in today's video, we're gonna see a fix for that, and let's jump right in. The topic of today is frame rate stabilization, and by the end of the video you will know how to get this two-dimensional bouncing ball that looks to have the same speed across all of the devices. So the frame rate will be stabilized across the devices. So first we need to know about the importance of frame rates. Okay, so frame rate is directly related to gameplay experience. So if you have any issues with the FPS of your game, it will be immediately noticeable to the players. When the FPS is too low, the gameplay starts lagging. But when the FPS is too high, it's basically draining a lot of energy from your system, and every game seems to have this optimal FPS range in which there is a good balance between how the game performs and how much energy it consumes from the system. You need to target that range for your game. Now, let's learn about which is suitable for higher FPS. So, mostly desktop and console games where the hardware is powerful is good enough to run high FPS games. And if you need real-time graphics and real-time gameplay in your video game, you would always prefer to have high FPS so that it's more noticeable to the players. Of course, if you need realistic physics simulation, then also you need a high FPS because physics requires a lot of background computations. Some of the examples include most AAA titles and certain fast-paced games and most modern games in general. So now let's learn about some of the games that are suitable for low FPS. So let's say you're targeting mobile or other handheld devices, then you need to be careful about how much energy your game is consuming, because if it consumes too much, it will be draining the battery faster, and we don't want that. The players don't want it either. So for mobile games, you should be targeting for a slightly lower FPS. If you're having a turn-based gameplay, then it's much simpler to have lowered FPS because you don't need to compute a lot of things real time, and you can optimize it. If a game has minimal animations or very little physics simulation, then also it's good to have a low FPS setting. Some examples include visual novels, deck building games, and point and click games. So most of them are not graphically intensive or physically intensive, so we choose to have a lower FPS in these cases. Right, now that you know about high and low FPS settings, let's understand how to stabilize FPS in J2ME. First of all, you need to remember this code that a fast device can run slower, but a slower device cannot run faster. That means is all of the stabilization techniques would be mostly designed for a faster device to make it run slower, and you should have a minimum hardware requirement range for your game that you're targeting, because a slow device will not be able to catch up to the speed of a faster one, right? Now, there's broadly two techniques that you could be using. Either you should be setting your FPS as a constant, or you can set your FPS to have a range, like a minimum and maximum FPS within which the game is nice to play. I think most modern games go with a ranged FPS approach, but in this video we'll learn about the constant FPS mode, because that is much more simple to implement, and in case of J2ME you would kind of be expecting it to run at a single constant FPS. So to understand this technique, basically you need to remember the game loop, right? And a game loop basically is at the heart of every game. You are looping certain functions over and over again, and every loop iteration corresponds to a frame. So in the diagram you can see I have marked down, let's assume over the duration of a loop, a slower device performs 4 tasks, 1, 2, 3, and 4. And let's say you have a faster device, so it will perform the same task at a faster speed. And at the end, what happens when the 4th task ends for a faster device, it usually jumps into the next loop iteration. That is what is causing our FPS issue. So if you're jumping immediately to the next iteration, it will increase the number of frames per second, because per second you are doing more loop iterations, you are drawing more frames. So what we need to instruct is our fast device should wait until the loop ends. For this, you have to manually compute what would be the start and end duration of a frame, and if there is any remaining time at the end of the loop, then you can make the device sleep for that much duration, and that should ideally solve our problem. Here is a code example of how it would look like. So the first thing we're computing is the time taken per frame. I call it milliseconds per frame, MSPF, which is just 1000 divided by the FPS. Here is our game loop. So the game loop is doing some physics updates and some graphic updates. And for the physics update, you should be passing in the time duration, right, for passing into the physical equation, that is delta t. And you can assume delta t is approximately equal to the MSPF. So the milliseconds drawn per frame is kind of what delta t would approximately be equal to, but it's not the exact definition of delta t. But in our case, since we're expecting the frame rate to be roughly constant over the entire gameplay, we can make this assumption. Now, once you're done with your physics and graphics code, at the end of the loop, you should calculate the frame end time. So this variable frame end keeps track of when the frame is supposed to end. And then you calculate the TZ, which is basically the time left, and that would be equal to frame end minus the current time. So if there is any time left, if TZ is positive, then you sleep the thread, right? You sleep it for that much amount of time, and that should ideally implement the final block of our game loop. Alright, I think we've done enough talking. Now it's time for a code demo. So we will be implementing these steps. First, we will define a constant FPS for our game. We'll go with 18 FPS, and Next thing is we'll identify which are the time dependent code, and we will make them use the MSPF value, milliseconds per frame, that we compute from our FPS. And finally, we will add the delay logic at the end of our game loop, so it will delay whenever necessary. Alright, so let's jump. Alright, so I have updated my IntelliJ to the 2025 edition, and we're good to go. So as always, we need to start by making a copy of our previous class. We'll be making a copy of the bouncing ball. Let's call it bouncing ball 2. Let's update it in the build script, and then we can do a Control C, Control V to create a copy. This is cool. Let's first start by defining our FPS. So final int FPS is equal to 18. Next thing is we need to identify which are the time dependent code here. So if you can see, mostly it's the physics that would be depending on time, because the other graphics related logic is independent of time. So we'll go by bounce ball first, and you'd see it's mostly doing a check on the position, so it's not depending on time. But if we go to the move ball method, here you can see we did a bit of a hack where we just added the velocity to the position. So if you recall, the actual equation for motion is actually like s equals ut plus half 8t squared. So in order to emulate this, we need to use the correct equation up here, and notice that we are assuming acceleration is equal to 0. So this entire second term becomes 0. And for the first term, we have ut, that is the initial velocity multiplied by the time taken. Now here we are not doing that multiplication, so by default it's multiplying it with 1, and I'm not setting it. That's kind of how math works. Let's add a t here for the time taken, and we can take this as an input. Right, now let's pass in the time here, but what should be the time duration? So the time duration you should be passing here is actually delta time, which is the time between the previous loop and the current loop run, and we'll use approximately a value that we can compute from this FPS constant. Let's try it out here. It's going to be final MSPF. It's milliseconds per frame, which is, let's say we'll make it a float, and this should be equal to 1000 divided by the FPS. Now we can use this value as our delta time, and that will lead you to approximately the result that we're expecting. But there are other techniques to improve the accuracy, but yeah, we'll ignore that for the sake of simplicity. Yes, we actually need to implement the weighting logic here, so we should be able to wait if needed. And for that, you need another variable to keep track of the frame ending times. Right, so let's define it. Let's call it long frame end. That is the time at which the frame ends. And we'll initialize it with the current time for now. Notice that we are defining it outside the game loop and we'll just be updating it inside. So every time we are done running these logic inside the game loop, we should calculate the next frame end value, that is the value where the frame is supposed to end. And this is going to be basically the previous frame end plus the MSBF. And you notice it's giving an error because of the data type mismatch. So let's convert it to a long first. So we can do it like this, or in a shorthand we can make it plus equals. So now frame end is equal to the value in basically milliseconds when we expect our frame to be ending. Right. Now there might be some value left. The current time may be less than this time. So we'll figure that out next. I'll say time left is equal to the frame end time minus whatever is our current time. This value is going to be positive in case the device is running faster. So that means all of these methods are executed fast and we still got some leftover time before the frame actually ends. Now we're going to check if the time left is greater than 0, it's positive, then let's wait for this time. And the way to wait is you do thread.sleep for the time left. Now you're going to notice another error coming up here, unhandled exception. So thread sleep throws a interrupted exception, which is generally called if the user is trying to close the program or to stop the thread while it is sleeping. So we'll try to surround it in try catch. To handle that, let's say try, and we'll add a catch block for the interrupted exception. And what we're going to do is anytime we encounter the exception, we'll simply exit our loop. Now this should do it for us. Let's try to run the app and see how it works. And as always, first I need to export my Java home to the correct position, and then we are going to do a Gradle W red ball emulate. You can see it opens up the emulator, and there we have it. The ball is moving a bit slower, but the real test is you have to try it out on a mobile device to see if the logic actually works, right? So what I'm gonna do is turn on my Bluetooth and transfer it to my phone. So if you see, it's jumping pretty much fine at the same speed in a mobile device. This looks cool. Now we realized that the logic actually works for a mobile device. Both of the devices are running the game at roughly the same speed. Now to make things a bit more interesting, let's actually add the X direction motion here as well. So what we're going to do is basically we'll go to the canvas class and make a copy of the y variables. We'll call it the x position and x velocity. Let's keep it as it is for now, and we're going to use it everywhere where we hard-coded the x values. Like this fill rectangle should now become an int of the x position, and inside the move ball we're also going to update the x position. So we're going to say x position is plus equals x velocity times t, same as we did for y velocity. And we are also going to do boundary checks in the x direction. So let's write it out. So if the x position is less than 0, or the x position is greater than the end of the screen, that would be defined by get width minus the diameter, we're going to do x velocity is equal to minus x velocity. Alright, so we have x position as well being updated in the logic. Let's try to run it once again and see how it works. So we'll do a red ball emulate, and there we have it, a nice red bouncing ball. Let's check it on the mobile device, how it works. So congratulations, we have achieved a constant FPS across all the devices. This is good progress. Alright, that's pretty much it for this video. And I've noticed there are some refactoring needed in our code base. It's getting a bit messier, so we'll try to fix those issues, and I'll share you the next plans over in the upcoming videos. But until then, we're pretty much done. Thank you so much for watching this until the end. Please like and share this video, and consider subscribing to my channel for more upcoming videos like this. Thank you.